Welcome everyone to this explainer on LogQL metric queries. If you've ever felt, completely overwhelmed by endless streams of text logs, or kind of struggled to turn those logs into actionable system metrics, well, you are in exactly the right place. By the time we wrap up here, you're going to know exactly how to transform that messy, unstructured log data into precise, highly visual indicators of your system's health. Let's get into it.
Okay, let's dive right into this. Here's our game plan. We'll start with logs versus metric queries, move into counting events over time, normalizing those with the rate function, grouping data with SumBy, and finally, we're going to put it all together to solve a real-world scenario involving a deployment error spike.
All right, part 1, logs versus metric queries. This is really the foundation of LogQL.
So, log queries basically act like a distributed grep. They return the actual text content of your log lines. And look, they're absolutely fantastic when you need to read a desperate stack trace at 2 a.m., but text just doesn't graph well, right? Metric queries, on the other hand, are the critical transformation you need for your dashboards and alerts in 2026. They extend those log queries by applying functions to calculate values, literally transforming those raw text occurrences into numeric range vectors. Now, what's really interesting about this slide is how Grafana leverages these distinct vectors to optimize dashboard performance. If you're building a stat panel to just show current status, Grafana uses an instant vector, grabbing just a single calculated value. But if you want a beautiful time series line graph, it utilizes a range vector. You can spot these by that bracketed duration suffix, like 5 minutes. It executes across the entire dashboard time range to generate a sequence of vectors that actually form your graph. Moving on to section 2, counting events over time. This is where we unlock log range aggregations. So the most common entry point for turning logs into metrics is count_overtime. It is absolutely the foundation for volume monitoring, essentially acting as a super straightforward event counter. It literally just tallies up every single log line that matches your criteria within a specific window of time. Simple, right? Let's deconstruct the syntax a bit. We start with our stream selector right inside the curly braces. Job equals MySQL. This tells Loki, hey, only look at logs from our MySQL database. Then we add our line filter, pipe equals error. This isolates only the lines actually containing the word error. And finally, that bracketed 5M at the very end, that defines our static 5-minute time window. Now, if you hit run on this query in Grafana Explore, you're not going to get lines of text. You simply get a number, like 37. This means exactly 37 errors were counted in that specific 5-minute window for our MySQL job. It's clean, it's purely numeric, and best of all, it's entirely graphable. All right, section 3, normalizing with the rate function. We're moving beyond just absolute volume here. Here's the thing. While counting is great, raw counts can seriously trick you. If total traffic drops overnight, well, your error count drops too, even if your actual failure rate is skyrocketing and the database is actively on fire. Enter the rate function. It calculates the per-second rate of log entries within your specified range. Site reliability engineering teams absolutely prioritize this function because it gives you a high-signal, normalized input. Your alerts apply consistently, regardless of whether the service is pushing peak traffic or operating at minimum scale. Let's move to the next step and see how this builds. We take the exact same stream selector and error filter from before with the exact same 5-minute window. But this time, we wrap the entire expression right inside the rate function. The math happening behind the scenes here is beautifully simple. Loki takes those 37 errors it found and simply divides them by the duration of the range in seconds. Since a 5-minute window is 300 seconds, 37 divided by 300 gives us exactly 0.123 errors per second. Now that is a high signal metric. Section 4, grouping data with SumBy. Time for some multidimensional vector aggregation. Okay, so often your metric queries are going to produce way too many time series. One for every unique combination of labels. Container, pod, instance, region, the whole shebang. We control this cardinality using SumBy. It's an aggregation operator that essentially drops all the labels you don't explicitly list, grouping and summing the metric values by the remaining dimensions. In modern observability, this is pretty much the gold standard for service-level comparisons. Here is exactly how we isolate that noise. We look at all logs in the production namespace, filter for errors, and get that per-second rate. But then, we wrap the entire result in SumBy app. This effectively tells Loki, listen,
I really don't care which pod or region these errors came from right now. Just group them together strictly by the application name. And this brilliantly illustrates why we do this. By breaking the data down this way, it immediately reveals that the payment service is experiencing the bulk of the failures, sitting at 0.15 errors per second, while the inventory service, perfectly healthy, at 0. It cuts through the noise instantly.
Section 5, Scenario Deployment Error Spike. This is the boss fight.
We've built up our foundational skills, so now it's time to put them under pressure. Imagine you're the first responder on call. A new code deployment just went out for the API. Suddenly, customer support escalates a frantic ticket asking, is the error rate actually increasing after the recent deployment? You need to answer this definitively, and you need to answer it right now.
So, methodically, you open up Grafana Explore. Step 1, you select the raw log stream for the API. Step 2, you filter that stream strictly for the word error. Step 3, you append your 5-minute time window. And finally, step 4, you wrap the entire thing in the rate function to normalize the data so those random traffic fluctuations don't trick you.
So the crucial point is, in mere seconds, this single line of LogQL transforms mountains of unstructured server text into a definitive answer. This exact syntax is what gives you the final analytical metric you need to get back to the support team.
You run that query and visualize it as a time series panel. The chart shows a perfectly flat, healthy baseline of 0.01 errors per second, and then an immediate, massive spike to 0.45 errors per second right at the exact end of the timeline. You now have definitive visual proof. That spike perfectly correlates with the recent deployment event.
I want to remind you of this vital quote from this source material. Alerts should be designed for the first responder. Mastering LogQL isn't just about, writing clever queries. Turning logs into high-signal metrics is ultimately about reducing alert fatigue, spotting regressions instantly, and making on-call rotations actually sustainable for your engineering teams.
We've covered the whole journey today, from simple log lines to normalized, actionable metrics using count over time, rate, and sum by. So I'll leave you with this final thought. If you can turn any raw text log into a high-signal metric in mere seconds, what hidden system bottlenecks are you going to uncover first? I highly encourage you to open up Grafana Play today and start testing these LogQL queries on your own. Thank you so much for joining me on this explainer, and hey, happy querying.